Alrighty, great. Welcome to the Talking Underwater podcast. I'm Lauren Del Ciello, Managing Editor for WQP, and I've got on the call today Scott Wilson, President and CEO of REGENESIS. Thanks for taking the time to chat with me today, Scott.
Well, nice to be here. Thanks very much for having me.
Yeah, I'm really looking forward to our discussion. So this month's episode of the podcast is all about PFAS. So I thought first and foremost, let's start pretty high level there. Of course, a lot of our listeners will know this background, but I think it's good to kind of establish where we're at. So first, high level, what is PFAS?
Well, PFAS is an acronym given for a group of chemicals that are perfluorinated or polyfluorinated alkyl substances is the technical term for it. And really what it is it's a mixture of compounds that are composed of a series of carbon atoms linked together, usually with a different substitute on one end, like an acid group on one end or a sulfonate group on one end. And then they're covered with fluorine molecules, fluorine atoms. And so the fluorine atoms and the carbon atoms are combined with a bond, and that bond is very, very, very difficult to break. It's one of the strongest bonds in nature. And so what you have is this mixture of molecules that were man-made called polyfluorinated alkyl substances that are composed of these chains of carbon atoms that are surrounded by fluorines with one end that's different. And really what that does is it imparts what's known as a surfactant-like property. And what that means is that they tend to act as very similar to soaps, with one end of the molecule wanting to stay inside of oils or non-water-like molecules, and the other end of it wants to stay in water. And so it acts sort of like a soap by drawing oils into water. But what's important is the longer chain PFAS, that is the PFAS molecules that are longer, they tend to really want to stay in fat or in oils and not into water. And what that means is that when they happen to come into the body or into an animal, for instance, it tends to want to stay in the fat or the non-water groups within the body and not be expelled from the body in urine or in respiration or anything like that. So what it does is it tends to build up over time, and this is called bioaccumulative. And that's one of the things that are really that's really a problem for us with PFAS molecules, is that these, particularly the longer chain ones, they tend to bioaccumulate and stay in the body and continue to increase in concentration. And because these carbon-fluorine bonds that are part of it are so difficult to break, sunlight doesn't break them, chemical oxidation doesn't break them, biodegradation is very, very difficult. There's only been one instance of biodegradation that's shown to work on degrading these compounds, that they just don't go away, and so they're known as forever chemicals. So two big problems: they don't degrade very fast, so they're forever chemicals as they're known. And secondly is they bioaccumulate inside the body, particularly the longer chain ones.
Beautiful, thank you. And the writer in me loves a good metaphor too, so thank you for that. So where can it be found, though? Anything surprising? Anything people wouldn't necessarily suspect?
Well, just one other thing about these is that there's thousands of these different types of PFAS, thousands and thousands. I mean, some people I've read the 5,000 plus, other places will say 9,000 plus, different conformations or types of these compounds. We call them PFAS or PFAS as the whole group. But, you asked, where do you find them? Well, they were actually first formulated by man, and they don't occur in nature. So they were formulated by man in the 1940s, and they came out initially as a coating to have a non-stick type of a coating, to make a non-stick type of a coating out of it. And then we also then man realized that these compounds were also fire retardant. We found out that they were also foaming. They made great foams. And so we also found out that they're good for not only non-sticking for Teflon type materials, but that could also be put onto clothing and have different attributes for passing water and not passing air and water and not passing other compounds for everything from odors to even cooking in materials. Anyway, so we found that we can find these in all sorts of compounds and all sorts of products. Just to name a few, of course, Teflon and nonstick for firefighting foams, surface coatings, water repellents. It goes on and on. There's all sorts of things. And just as a comment, a lot of big corporations have been vilified for making these compounds, particularly recently in the press. But you have to put it in context. If you coming off of World War II, when these compounds were first available, it was better living through chemistry was a moniker, right? So people were looking to new chemical compounds to better our daily lives. Look at, for instance, women started wearing nylon stockings instead of silk stockings, right? Men started wearing Banlon shirts instead of wool or cotton. These were all new inventions of chemistry. And lo and behold, the housewife of the 50s could now or 60s could spray a coating on their pan and fry an egg without having it stick. Mm-hmm. So, it made our lives all better. And yet now we're kind of realizing that maybe it was a little overdone and we went overboard. Just one other comment is, back then we didn't have the analytical techniques to even know how soluble these compounds were, let alone the diagnostic tools that medicine has now to determine what's toxic and what's not. And so, now we're looking at these compounds and saying, boy, they might be generating some toxic. They might have toxic properties even at very, very, very low concentrations, parts per trillion, that we were only recently able to even measure.
Right. Yeah, of course. It certainly makes you wonder what else we think is a good thing now that we may have some unsavory, surprising information about in the future.
Absolutely. Yeah, for sure, Lauren.
So I see you have quite a background in the groundwater side of the water industry as well, some past experience with NGWA and those folks who are wonderful. So I'm particularly interested to how you approach this question is, how does PFAS contamination impact groundwater professionals differently than surface water, and kind of what unique challenges exist in treatment and disposal there?
Great. Well, so, PFAS can get into the environment in all sorts of ways. Mm-hmm. During manufacturing, it can be expelled through smokestacks into the air. It can be held in tanks and leak into the subsurface from tanks into soils and then groundwater. It can wash off the surface of properties into surface waters. So there's lots of ways it can get into the environment. And I think one of the things that we have to, just to put in perspective, is that, groundwater, that is well water derived from the subsurface and pulled to the surface vis-a-vis wells, that's used for about 51%, or I should say drinking water in the United States is composed, 51% of it comes from groundwater. In the rural communities, it's over 90% of their drinking water is coming from groundwater out of wells. So, groundwater that's impacted by PFAS is a big deal. It's a big issue. And so for groundwater professionals, that is people that are in the business of restoring polluted groundwater or using groundwater as a resource, PFAS contamination is a real problem. These compounds get into groundwater, as I mentioned. It could be from rain. It could be from storm water or runoff that gets down into the ground and into groundwater. Those contaminants, once they're there, there's only a few ways to treat them. And the real problem with anything in groundwater is the potential for it to hit a surface water body or for it to impact a receptor for drinking water. And The real challenge to the groundwater professional is how do I eliminate the risk of this PFAS from migrating down gradient in the subsurface and impacting a drinking water supply or impacting a surface water body. And many people aren't familiar with what groundwater is. Groundwater itself is nothing more than water that's moving into the subsurface by rain or however migrating down, and then it actually is just filling the pores of the soil or filling the pores of the rock. That's groundwater. And if there's more groundwater in one area, it's going to be at a higher elevation than others. It'll migrate down gradient, down gravity, if you will. So groundwater is generally always moving, and if there's PFAS in that groundwater, it's what we call a groundwater plume, P-L-U-M-E, and you have this plume of contamination. And as it's migrating down gradient, the last thing you want it to do is to impact a surface water body like a stream or a lake, or a drinking water body. I should say a drinking water supply, like a recovery well for a municipal drinking water or domestic water supply. And so, there's several ways to treat that, but the goal is always the same, and that is to eliminate the risk of that migration to impact those receptors. The typical way of doing it is to put in an interception well or a line of interception wells and pull that water to the surface. Once you pull it to the surface, you've cut off that plume, so it's no longer migrating down gradient. But now you have to treat that water. You have millions of gallons of water coming to the surface. You have to filter it through filters. And when you filter it through filters, then what do you do with the filters? Currently, you have to dispose of them either in a landfill or send them off to an incineration facility and have them incinerated. It's really the only two ways you can handle it. And right now, landfills are becoming very short supply. Most landfill operators don't want the responsibility of having to have somebody else's PFAS contamination in their landfill. And about a year ago, there was an incinerator that was shown it was supposedly a key incinerator for destroying PFAS. It was shown that the incinerator was actually emitting PFAS or partially combusted PFAS into the air, and it was raining down on the city.
Oh my gosh.
So there's questions as to just how well this can be incinerated. And that work was done by Bennington College, and it was in New York where the incinerator was. As a result of that, there's been several bills in U.S. Congress to ban the incineration of PFAS, and several states have either pending legislation or passed legislation on banning their incineration of PFAS. So the question is, what do you do with it once you've filtered it out of the water that you've brought to the surface? One other thing that I'll mention is that the Biden administration is moving forward. They've claimed that they've stated that they're moving forward with making two specific PFAS molecules. These are the longer chain ones that are more bioaccumulative. It's PFOA and PFOS. That's PFOA and PFOS. They're planning on making those two compounds a hazardous material under the Safe Drinking Water Act. And if that is done, that will mean that there is an MCL, which is the maximum concentration limit that can't be surpassed for drinking water. And right now, the EPA does not regulate any PFAS. The only thing they have is they have what's called a health advisory level. And they've said the health advisory level for PFOA and PFOS combined of 70 parts per trillion is less than that is acceptable. Over that's not acceptable. But now it looks like the administration wants to actually put in formal regulations under the Safe Drinking Water Act and making these hazardous materials, the PFOA and PFAS hazardous materials, and putting formal regulations on them. If that occurs, it generally follows that under what's known as the Comprehensive Environmental Cleanup and Liability Act, CERCLA, also known as Superfund, it generally follows that under Superfund, that those compounds will be considered a hazardous material. And if that's the case, disposing of that canister of that filter cartridge, or that filtrate material that you've pulled the PFAS out with, that's going to be incredibly expensive to dispose and handle, because now it's a hazardous material and has to be taken to a formal hazardous material storage or disposal facility. Extremely expensive. So anyway, if you need to treat PFAS in the groundwater right now, typical method is to put in a pumping system, pull it to the surface, filter it out, and either send it off to be burned or send it off to a disposal facility. And what's emerging now? There's new technologies that can actually be placed right in the subsurface. You can inject forms of colloidal activated carbon, and it will convert portions of the subsurface into filter zones, so that as the water moves through the aquifer itself, the PFAS can be filtered out in place, where it just stays right in that one zone and eliminates the risk of it moving down gradient at all. And this is gaining in popularity now. It's called colloidal activated carbon. That's gaining in popularity and is actually being used. I think it's like 20 projects now it's been used on. And these range from small pilot demonstrations to large refinery sites where in thousands of lineal feet of activated carbon treatment zone has been placed in the subsurface, and it's blocking the PFAS from migrating into surface waters and or drinking water supply wells. So that's another way to do it.
Yeah, the disposal issue is something I definitely wanted to dig into more, because that really creates a circular issue for PFAS. It's one of the biggest obstacles to effective treatment. But we're getting a little close on time, so I just want to ask you one more question, which you did kind of touch on this a little bit earlier when you were kind of talking about the relationships between the different aspects of water and how PFAS impacts that. But on the Talking Underwater podcast, we often talk about this concept of one water, how all aspects of the water cycle, from wastewater to drinking to stormwater, are interconnected. So how is PFAS a one water issue?
Well, I'll tell you how it's a one water issue. There was just recently a study that was published that actually showed it was performed by the Integrated Deposition Network, which is funded by the EPA. It's run out of the University of Indiana, or Indiana University, and they actually looked at what's happening in the Great Lakes area, and they tested 6 different sites within the Great Lakes. They tested rainwater coming down, and they actually showed that in the rainwater at the 6 sites, the concentration of PFAS in the rainwater samples collected ranged from 100 to 400 parts per trillion. And right now, the health advisory limit by the U.S. EPA is 70. So the rainwater raining down is already exceeding the health advisory standard. And that's just, that, Lauren, is actually dropping into the soil and then moving right into the groundwater that we have to drink. Yep. 98% of the people within the U.S., their blood has detectable amounts of PFAS in it. And so the rain comes down, goes into the soil, drains into the groundwater, gets into the lakes, gets into drinking water, gets into people. It's all one big cycle.
You get it. I'm with you. Absolutely.
Yeah.
All right.
And, yes, please go ahead.
No, go ahead and finish up your thoughts. Certainly, Scott.
Well, I was just going to say that it's been found in polar bears, the blood in polar bears. It's been found in seals, sea lions. It's everywhere. And what we have to do is we have to break the chain before it gets into the aquatic environment. We have to break the chain before it gets into our bodies through drinking water and showering, where we inhale it, and our food supply. And so I think it'll be a big task for us, particularly in light of the prevalence of it throughout the world. but it's one of those things that we have to find a solution for it. Otherwise, it'll just continue to bioaccumulate and move up the food chain.
Well, on a solution-oriented note is a great way to end. So I thank you for your time today, Scott, and sharing your insight with Talking Underwater podcast.
Well, thank you. I appreciate being here.